My interest in science started with a bit of a conundrum. After watching a Horizon programme on the BBC, Who's Afraid of a Big Black Hole, I thought that if time actually does stop in the singularity of a black hole, could all black holes be at the same place, the opposite to the Big Bang, the end of time itself? A rather absurd thought, but one that sent me on an amazing journey of discovery. At first it was just educational, as my autodidactic mining of the internet uncovered the treasures of past and present polymaths. I never imagined, for one moment, that it would lead me to question the accepted physics or discover a previously unknown hidden variable in the space-time continuum, one that could lead to new understanding of the whole universe. But that is just what I believe I have now discovered. I call my hypothesis the fractal topology of space-time theory. The name is derived from the way that both space and time appears to have a fractal property to it. To quote the Fractal Foundation's website, "A fractal is a never-ending pattern. Fractals are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback loop. Driven by recursion, fractals are images of dynamic systems, the pictures of chaos." And to demonstrate this visually, I've created this simple dynamic recursive pattern I call diminishing time. Topology, because we are dealing with the dynamic geometry of both space and time. Spacetime is an amalgamation of the spatial and temporal nature of our reality. Many recognize that the first to formalize mathematically the notion that space and time are not separate was Hermann Minkowski, although not overly impressed with his now famous student of his, Albert Einstein. He was to later propose that the best way to understand Einstein's special theory of relativity was to use a four-dimensional space that he called spacetime. An abstract of this theory is that all the components of space and time are changing over time as time slows down relative to the past. In this theory, instead of space expanding, all matter is shrinking relative to the past for all observers. At the same time, time itself slows down, and I see this as a shrinking of the relative elapsed time relative to the past. Local distances shrink with our rulers, unnoticed as past distances are observed to be getting longer relative to the present and future observers. The speed of light, although we will always measure it to be the same speed, is slowing down relative to the past. This is the hidden variable of the space-time continuum. Synchronously, there exists a time and distance asymmetry that have an equivalence. Relative to Earth, a geostationary satellite's measuring rods will be longer, making measured distances through space shorter, while experiencing more elapsed time, while on Earth, relatively shorter measuring rods will make measured distances longer, in less elapsed time. My task now is to explain the type of absolute space that is neither Euclidean or Newtonian that time and distances are relative to. Now let us first look at that Earth-satellite relationship in a little more detail. Gravity slows down time. On the Moon, with less gravity, time will run a tiny bit faster. Moving away from Earth's centre will speed up time as gravity weakens. Time runs faster at the top of a building relative to time at the bottom. The time dilation effects that we are likely to experience either gravitationally or kinematically are tiny. Even if time were to slow in a more significant manner we would still experience every second as a second and measure it as a precise second. Even the height of the International Space Station makes very little difference. In fact, time is relatively slower on the International Space Station relative to that on Earth due to high speed that it has to travel to keep it in free fall. The velocity of an object has the opposite effect to an increase in altitude. And here, time dilation, due to the velocity necessary to stay in a low Earth orbit, makes time run slower on the International Space Station relative to that on Earth, orbiting nearly 16 times a day at over 17,000 miles per hour. An orbiting satellite that is further away from Earth will have a slower orbiting velocity and less gravitational influence, and by the time we get to the GPS satellites at nearly 12,000 miles up, or to a geostationary orbit at about 22,250 miles out, time is running relatively faster than on Earth. If I were to draw an imaginary line 90 degrees to the rotational axis from the centre of the Earth and intersect the imaginary line of the equator, extending it up past the path of the geostationary satellite's orbit, and fix it at the local noon position on Earth, so that, if the line were a pencil, it would draw a line on the equator as the Earth rotates. At midday, the satellite at position 2 and its corresponding position on Earth at position 1 will pass that imaginary line at a synchronous moment in time. We will call it moment A. This assumes a priori that a moment can transcend information in the speed of light. The next day they both synchronously cross the imaginary line again at moment B. Because time dilation is less on the satellite relative to time on the Earth, the satellite experiences more elapsed time between the two moments relative to Earth's less elapsed time. If at moment A on Earth and moment A on the satellite we were to simultaneously send two light signals and then see how far each signal could travel during the elapsed time from moment A to moment B, we find that because the satellite experienced more time between the two moments, the light signal can travel further, with an extra 45 nanoseconds of time relative to Earth. The light from the satellite can travel a further 44 feet 2 inches. Not far when you consider light travels at 186,000 miles per second, but nonetheless it is relatively faster. We have to consider the rate that time runs at is relative to the observer, and so it is from how far away a photon can be emitted from at moment A to reach the observer at moment B that should be considered. Although the measured speed of light is the same at position 1 and position 2, the speed of light is relatively slower on the Earth, not for any reason like the refractive index of the insignificant amount of air surrounding Earth, but because of the difference in the rate of time between the two observers. A signal sent from the Earth to the satellite and back will take longer than the signal sent from the satellite to the Earth and back. This is because we define the SI units of distance, like the meter, with the speed of light, and so the distance between the Earth and the satellite is relatively further than the distance from the satellite to the Earth. The satellite does not have two positions at the same moment. It is a difference in the distance scale due to the relatively slower speed of light on Earth when synchronously compared to that on the satellite. The satellite sees less distance and more elapsed time, while the Earth sees more distance and less elapsed time. In order to maintain this synchronicity in a dynamic system that includes observations of distant galaxies, all that is required is that time is slowing down over time for all observers. All atoms would be relatively shrinking over time along with all observers' light speed measuring rods. Atoms must be shrinking with our measuring rods, or our measuring rods would not be shrinking. The distance from the Earth to the satellite at moment A will be measurably the same at moment B, but that distance will be relatively shorter due to time slowing down over time, in the same way that the speed of light is relatively slower, yet measured as the same speed over time. The distance from the Earth to the satellite at moment B will be relatively shorter, yet measured the same. All gravity-bound objects will have this hidden peculiar movement, giving our own galaxy and local galaxies in our cluster a hidden from us shrinkage. All actual distances are shorter and all objects smaller in the future relative to their past, making past time distances, that's everything we see, relatively longer compared to now and the future. The dimensional shrinkage of a planet will cause gravity at the surface to increase. Gravity may have increased very gradually over millions of years here on Earth. We know the narrative of the universe unfolds in time, and logically this predicates that there must be a distinction between past, present and future, something that can be afforded with a type of fractal geometry. Time is part of the dimensionality of our universe. For instance, spatially, we have the dimensions x, y and z, and objects exist as three-dimensional entities. And famously, Richard Feynman once said, "Time is what carries on when everything else stops." Yet we cannot describe movement without time. However, we are so used to seeing time as a one-directional line on graphs and diagrams that we tend to ignore the fact that movement through time is as multidimensional as the moving objects themselves. As the now moment changes, multidimensional movement emerges. So I like to think of time as something that is fundamentally three-dimensional. According to Einstein, the speed of light is always measured the same, regardless of any motion that can be attributed to the light source. Whilst postulating the consequences of this, he developed the theory of special relativity. If all observers have to agree on the speed of light, then they will have to disagree about all the components of space and time. Here we have Alice, and for now she is stationary. If she fires her photon from the nose of her spacecraft, it will travel 12 light seconds in 12 seconds. Now if Bob, in his identical spacecraft, were to fire his photon simultaneously with Alice as he passes, you will notice that relative to Bob, the photon appears to only travel 6 light seconds in 12 seconds. But we know that must be wrong, and part of the answer for why is that the clocks aboard Bob's spacecraft will be running more slowly. And if Bob's clock were to run half as fast, then the problem would be solved, as Bob would now report that the photon has travelled 6 light seconds in 6 seconds. But it turns out that the slowing of clocks is not enough to account for the full change in distance. In special relativity, Einstein shows us how time slows down for a moving object. A simple visualization used in teaching is to have a stationary photon clock where we imagine a photon bouncing between two mirrors, and an identical one that we'll give to Bob so he can put it into motion. Because the speed of light is a constant relative to the stationary clock, the photon in the moving clock has further to travel between bounces, making the elapsed time between the bounces longer and therefore slower. Now, when Bob passes Alice will see Bob's clock run more slowly. But I must point out that in Einstein's special relativity, Bob could consider himself as being the stationary one, and so from Bob's perspective, Alice's clock would be the one that is running more slowly. According to Einstein, the flow of time is completely relative. Earlier, I said that the slowing of Bob's clock was not enough to account for the whole distance. It turns out that Bob would experience 9 seconds during the elapsed time that his photon travelled. The other phenomenon of Einstein's postulate is length contraction. Bob and his ship would contract in length along with the distances, making his 9 light seconds just enough to cover the right distance. So now, as Bob passes, he experiences the photon travelling 9 light seconds in 9 seconds, the same 1 light second per second as Alice. Time dilation has been proved time and again. My sat-nav would not function without the technology that allows for it. However, I was a little uneasy with the postulate that as Alice and Bob here were to pass one another, that both views are simultaneously correct. Above the door to the Royal Institute of Science are the words nullius in verba, which roughly translates as take nobody's word for it, and so I embarked on a bit of divergent thinking. When Bob accelerates, distances become shorter relative to when he was stationary, or slower even. When thinking about how distances shorten during time dilation, an ambulance passed by. And that started me thinking about the Doppler effect, and this diagram appeared in my mind. But with light waves, instead of a higher and lower pitch, we have a shift towards the blue with wavelengths getting shorter, and a shift towards the red with the wavelengths getting longer. And because of the association that light has with distance, I imagined shorter and longer wavelengths with shorter and longer distances. But distances cannot be simultaneously both longer and shorter to Bob. But then I thought, perhaps they do not have to be. We just have to think of them as being separated into past and future distances. The future distance no longer has to pertain to any one direction or dimension, because the past and the future are now separated by the present moment in time. They are separated by time, three-dimensional time and distance. As Bob accelerates, all past distances will be longer and all future distances will be shorter. We know time dilation is a real phenomenon, and if we follow Bob in his accelerating frame of reference into the future, where all distances are shorter, he will not notice them getting shorter, because all the measurements of his ship are shrinking along with the time on his watch or unnoticeable to Bob. I call this an isomorphic shrinkage of matter. The shrinkage is just the same in all dimensions. Comparing this to length contraction, we still maintain the criteria for a light second to remain a light second. Bob accelerating causes his time to slow down and all future distances to shrink. But neither Bob or anyone else can see into the future. What we all see are things in the past. The greater the distance of an object, the further back in time that object was when it emitted the light that we see. The quicker Bob accelerates, the faster distant objects recede away, as past time distances increase in every direction, with the furthest objects receding the fastest. This now looks far too much like our expanding universe to be a coincidence. Now, I'm not suggesting for one moment that Bob's acceleration is causing the universe to expand, but it could be making it appear to expand faster as time for him slows down relative to when he was stationary. This acceleration of the expansion is a special case for Bob the observer. My next leap of the imagination was to link time actually slowing down over time homogeneously over the entire observable universe and become a general case for the causation of the actual expansion without the need for Einstein's cosmological constant that, in his own words, was an ad hoc idea to necessitate a static universe. When it became apparent that the universe was expanding, he later referred to it as his biggest blunder. Although now resurrected, it is what we now commonly refer to as dark energy, that ethereal, mysterious force. When we consider two divergent histories of differing reference frames, such as in the twins paradox thought experiment, we can see that a Hubble constant peculiar to the observer's frame of reference can solve the apparent paradox. Bob goes blasting off in his spaceship and leaves his twin sister Alice at home on Earth and accelerates to relativistic velocities. Although we know that it is Bob that is moving at such velocity that his time is running slower relative to Alice, it is a legitimate relativistic view for Bob to consider that it is Alice and the Earth that is moving away and then back to him. This graph shows the problem. The red line represents Bob's journey, and apart from the periods of acceleration and deceleration, Bob and Alice can consider the other as stationary, and the apparent paradox is that Alice ages more. So why, if both views are valid? I am now going to use that same past and future distance scale diagram and include Alice, because Bob and Alice both end up at the same place and time with the same length rulers. They both see the same expansion of the universe at any one moment, but as Bob travels at relativistic speed during the elapsed time, he experiences less time than Alice because his time is running synchronously slower than Alice's. As Bob's clock is slower, the expansion is faster, and his dimensional shrinkage is also faster. So they both agree about how much the universe has expanded and the size of their constituent atoms. Although Alice does not see the universe expand so rapidly as Bob, she is seeing it expand more slowly over the longer period of her elapsed Earth time, in such a way that when Bob returns, they have both seen the universe expand by the same amount but at different rates. Therefore, The rate of time can be something measurable as long as you can measure the Hubble constant. This makes time something that is real and not just a persistent illusion. It may run at different rates, but it is the same now moment in time everywhere. You can travel through time at different rates, but it is the same time that you are travelling through. We saw earlier with the photon clock how time runs slower for Bob. However, with the isomorphic shrinkage in Bob's travelling frame, all distances are simultaneously shorter at the spontaneous now moment of time, so we have to adjust Bob's photon travel to fit with the difference of scale between the divergent reference frames. If, that is, we are to see how Bob experiences time in the same way as Alice. However, they are not the same as this bouncing in unison depiction, because the light in Bob's frame of reference is travelling relatively slower, and so Bob experiences less elapsed time than Alice, like the pedals of a bicycle going slower than the wheels, synchronously differentiable. The rate of time in our solar system is dominated by our Sun, and relative to Earth, the Sun is about 1,000,000 times bigger. A white dwarf star is about the size of Earth, with the mass of a star, so it has a density about 1,000,000 times higher, and time dilation will be significantly greater than for our Sun-dominated solar system. The more dense the object, the greater the time dilation. The most dense objects in the universe are the black holes. The progression in density assimilates an evolutionary progression. The progression follows a fractal pattern, a fractal being an object or quantity that displays self-similarity. This Brackenfern fond, when cut into pinnae, pinnules and leaflets, display self-similarity in their level of description progressively down the fractal depth to the lowest level of description, in this case the leaflet. The evolutionary fractal depth of the stars goes from the primordial generation 3 stars down to the fractal prime, the black hole. All the components of space and time follow this fractal pattern relative to the observing object. But if the components of space and time are to follow this fractal progression, they will tend towards infinity and become infinite if the observing object is a black hole at the fractal prime. Would not the infinite gravity, for instance, swallow the entire universe? Well, no. A black hole singularity is when the object is so dense that the radius is equal to 0, where time stands still. Although gravity will be infinite, it is only infinite at the surface, which is pretty academic, as the surface area of a sphere with a 0 radius is of course 0. It would also only be infinite for the elapsed time, which would be also 0. Swap our Sun with a white dwarf star of the same mass and our orbit would not change. The gravity at the surface of the white dwarf star may be 1,000,000 times higher, but it would have the same effect as our Sun at our orbital distance. The same applies if we were to swap it for a black hole of the same mass. With a differentiable synchronicity of simultaneity, a now moment of time can pervade the whole universe, even where time has stopped. Earth is at a deeper fractal depth than a geostationary satellite, and the distance asymmetry at a stationary frozen moment in time is not a positional difference, but a difference in the scale between the Earth and the satellite. And vice versa. a scale differential that is changing over time, a hidden variable of all the components of space and time. I have now described two different ways that time changes the scale of space-time. It changes over time from past to future, and there is also a now moment where there is a simultaneous scale differential. If we bring the satellite back to Earth, during the time it takes to get it back, the scale differential will resolve. Here we have a simple model where each galaxy depicted here would represent a galaxy cluster. The rate that space expands is normally measured in kilometers per second per megaparsec. A parsec is about 3.3 light years. So, at a million times further, a megaparsec is a long way indeed. And if we draw a circle with a radius of 1 megaparsec, anything at that distance will have an apparent velocity of about 70 kilometers per second, and twice that velocity at 2 megaparsec, and 210 kilometers per second at 3 megaparsec, and so on with a linear progression. In this very much sped up animation, you'll notice that each galaxy cluster moves directly away from the observer. At this scale, it would take millions of years for any galaxy cluster to cross any of the lines depicted here. We do not consider that any galaxy cluster is moving relative to their local space. The apparent recessional velocity is considered to be due to space itself that is expanding. One of the most popular analogies for this phenomenon is to have buttons stuck to the surface of a balloon that are supposed to represent galaxies that do not expand but do separate from one another as the balloon expands. When the Hubble Space Telescope took a deep field image of this apparently empty area of space, it revealed many more galaxies at distances that were not predicted. The numbers represent the redshift value of some of the most distant. The recessional velocity of these galaxies are more than twice the speed of light. The distance from an observer where objects appear to recede faster than light is called the Hubble sphere. Any observer will have their own Hubble sphere. It must be stressed that nothing is actually travelling faster than light through space, for it is space itself that is expanding relative to the observer's increasing distance scale. Nonetheless, relative to an observer, things beyond the Hubble sphere are receding faster than light. Common sense would say that nothing beyond that interface between luminal and superluminal recession should be visible. But the Hubble Space Telescope has given us proof that we can. And the way that our current understanding explains this apparent paradox is in the way that they think the Hubble sphere expands with space. For instance, if we take these galaxies and imagine that, relative to the observer, they are now in space that is receding faster than light. So, not only are the galaxies moving away with superluminal recession, even the light emitted in the direction of the observer is going the wrong way to be observable. However, current theories claim that as space expands for the observer, the Hubble sphere also expands, and once the Hubble sphere has caught up with the photons from the receding galaxies, they then become luminal, relative to the observer, who then eventually can see the galaxies. But I see a problem with that hypothesis. The expansion of the universe is said to be speeding up, and so the recessional velocity at every megaparsec interval will be getting faster, like so. But we could also say that the distance to those particular recessional velocities are getting shorter over time, so that it is the galaxies closer to us that are getting to 70 as it speeds up. It stands to reason that if you have two cars and one accelerates faster than the other, it would get to 60 miles an hour in a shorter time and a shorter distance. The Hubble sphere is a distance to a certain velocity, the speed of light. So, as the universe expands ever faster, the Hubble sphere will decrease in size. The reason we can see beyond the Hubble sphere is because photons are in a superposition and their velocity is transfinite. Like a black hole, a photon is at the fractal prime, and so from the moment it is emitted to the moment it is absorbed, it experiences no elapsed time, inferring an instantaneous infinite velocity. It is at an infinite distance from everything that is in the past. On the other hand, future distances are zero, as it is already at the destination the moment it leaves, inferring that it is stationary. When it leaves the past, the future does not yet exist, so its position is uncertain, as in the Heisenberg's uncertainty principle. Its velocity when absorbed is relative to the fractal depth of the observer, and that is always c, the constant speed of light. The Hubble sphere, then, is not something relative to the past, but rather a distance limit to where the observer's light can reach in the observer's future. When we detect a black hole, it may not be at its fractal prime. We just need to be beyond that object's Hubble sphere. To have a now moment in time, we need to have an absolute space. Although time and space are not absolute in a Newtonian way, it is absolute if you make corrections for the elapsed time and matter shrinkage relative to the observer. In a toy model, represented by this slide, we can see that galaxy A and B do not change their position in absolute space, but they do have an apparent separation due to the change in the homogeneous distance scale change over time. The stars in a galaxy will have a peculiar movement through space towards the centre of their galaxy, a movement hidden by the shrinkage of each and every atom as the elapsed time gets less and matter shrinks over time. In this toy model, the visual effect is down to the shrinkage of matter. Although 70 kilometers per second seems very fast, if you scale down the volume of space with the radius of 1 megaparsec to the volume of the Earth with a radius of just over 6,000 kilometers, the surface of the Earth relative to the centre would be racing away with a velocity of, well, a mere 0.46 millimeters every year. So, if we were to exchange the expansion of space with the isomorphic shrinkage of all observable matter, our Earth would have to be shrinking by less than a millimeter per year. Now, more and more cosmologists are believing that the universe is infinite. I never thought otherwise. But all the evidence suggests that it had a genesis moment where time started, and also that time can stop in a black hole. And it sounds like time is somehow finite, and that's a paradox. If the rate of time is slowing down over time, it implies that it will stop altogether, like in a heat death. But if time is infinitely fast at the beginning and infinitely slow at the end, then the progression is transfinite. That means everywhere in between is halfway through time. And the way that works is the age of the universe is its elapsed time since the beginning, relative to your time now, which is running slower than it was at the beginning. Halfway back in time, for every second a day, they would experience too. The Hubble constant would be half as fast, and the way we calculate the age of the universe with the standard model, a slower Hubble constant would equate to an older universe in our past. So as we go forwards in time, our time slows down and the universe appears to be getting younger. Of course, the universe is not really getting younger. We just need to make corrections for the co-moving time scale of transfinite time, and by doing that, the age of the universe becomes infinite when the rate of time was infinite at our genesis moment, and effectively ends when the rate of time becomes infinitely slow. Time has another level of description in that things like Alice and Bob's divergent histories in the twins paradox, or time running at different rates simultaneously, like the satellite and the Earth. When we look up into the sky at night, we are looking into the past, and that is why I have drawn this simple light cone diagram this way round. The cosmic microwave background is the limit to our visible horizon. We cannot see into the future, and although the present has an infinite volume, we can only see or hear things from the past. We are not contained in our past light cone. Our sun does not directly bask in its own past light. There is not a bit of the cosmic microwave background that would become our galaxy, or any other galaxy or quasar we see, for the background radiation is much older light than the light from those objects. It is, however, light from matter that shares the same genesis moment as all those younger things that we do see. For something to come from nothing is not, in my opinion, an acceptable idea, and neither is the notion that time had a beginning either, although I do believe that our genesis moment was the beginning of our time for all that we see. The explanation that I would like to propose here is that we are part of something infinite that had a genesis moment, but that we are part of is not the totality of existence, and that there are infinitely many such genesis moments from before and after ours. Think of it as the Big Bang that has never stopped, with each new genesis moment separated by the infinity of the previous. We can now consider the progenitor of time as a continuum that has always had an existence. To help visualize this fractal topology of spacetime, I have transformed our visible universe into an infinite nested set by turning this past light cone into a segmented disk, with the observer in the center where this disk world would represent our observable sphere. As time slows down over time, this set descends through time to an ever lower fractal depth, where distances were relatively longer in the past, and will be relatively shorter in the future, where in the past, although the speed of light would have been measured the same as it is now, it was relatively faster. We can imagine the history of our nested set, where we once had an existence at the higher fractal depth, but where we now no longer exist. The observable to us part of the universe is a finite part of something that is infinite in extent, and so extends beyond the cosmic microwave background. In one single moment it all had its origin and has evolved over time. But I do not believe it is the totality of existence of all space-time. This depicts what I call our eon of time, a phrase I borrowed from Sir Roger Penrose, and is one of infinitely many eons of time that exist from before and since our genesis moment, a genesis moment that happened everywhere in our infinite aeon of time. I will refer to the progenitor continuum as a white hole singularity, being opposite to a black hole type singularity. as all eons of time progress down the fractal depth, all matter appears to be heading for a black hole type of singularity. And not believing that time can actually stop, I like to think that there is just the one singularity with two poles like a magnet. The singularity of a cyclical universe. The singularity. The idea that the universe is both creative and destructive in a cyclical, self-reflexive way is not new. It is synonymous with the self-reflexivity of an ancient Egyptian serpent, the Ouroboros. I just find it interesting that such an ancient civilization would depict even their gods inside that emblematic symbol. It is believed that when all our matter emerged from our genesis moment, an equal amount of antimatter also emerged like a mirror image. But there seems very little evidence of it left now. When matter and antimatter comes into contact with one another, they annihilate, releasing all the energy of both forms of matter in a huge flash, and it is thought that this actually happened just after our genesis moment, which then somehow left more matter than antimatter behind in an unequal way. But I think a better solution is if, as they simultaneously emerge from the singularity, both are infinite and as such separated by their infinity, their simultaneous eon of time that I believe would remain separated yet entangled until their end. This pie chart represents an eon of time that I will animate from start to finish. The yellow represents all the matter and the space within. Over time we have less space within the matter and more space outside the matter. I like to think of it as the future inside our atoms and the present on the surface and the past everywhere outside. Then we can see that the future shrinks as the past expands. As every atom shrinks, all mass becomes more and more concentrated. But if we think of space as unchanging holistically, the mass density remains the same until the fractal prime ushers in a new beginning with a jump. As an eon of transfinite time emerges with the matter, so too does an entangled eon of transfinite antimatter. They are like identical twins that never meet until the end of their transfinite cycle, where one can imagine in this case a matter eon of time becoming an antimatter eon of time in its rebirth and vice versa. Of course, there are infinitely many of these eon pairs that make up our universe with its continuum of emergence. I believe that this nascent theory has the potential to solve many problems inherent with the current standard model. Putting time as a fundamental reality with a well-defined past, present and future back into physics is, I believe, one of its main attributes. The apparent expansion needs no hidden energy. The time and distance asymmetry between differing fractal depths, along with the hidden peculiar movement attributed to the hidden variable due to the slowing of the speed of light over time, should account for the effects attributed now to dark matter. With this theory, there is no flatness problem, as the mass density remains holistically unchanged and varying only at a local level. Thank you for viewing this presentation. With the availability of emerging information, the novel ideas expressed here, nurtured without prejudice to the usual former knowledge, may lack the vigour of a well-written scientific paper, yet this way of thinking, without the lock-in bias, may be what is needed most of all.